Welcome to today's Explainer. Get ready because we're going to completely change how you view the physical world around you. I mean, have you ever actually stopped to wonder why a heavy box is just so hard to push? Or, on a much grander scale, how a massive rocket actually propels itself into the totally empty vacuum of space? Well, it turns out the answers lie in just a few incredibly elegant rules that literally govern our entire universe. Today, we're unraveling the mechanics of motion. We'll be taking you all the way from a simple falling book to the sheer complexity of orbital dynamics. Let's get into it. So, here's our game plan for today. We're looking at 1. The force of history. 2. Newton's 3 laws. 3. The momentum concept. 4. Mass versus weight. And finally, 5. Measuring our world. All right, let's jump right into section 1, the force of history. So, what is the natural state of an object? Really think about that for a second. If you're pushing a heavy box across a rough floor and you suddenly stop pushing, well, the box stops moving, right? Because of everyday experiences exactly like this, the brilliant Greek philosopher Aristotle assumed that an object's natural state was simply to be at rest. He figured that a constant, active force was absolutely necessary to make something move, and more importantly, to keep it moving. And honestly, based on what we see every single day, that feels incredibly intuitive. But here is where it gets really interesting. Nearly 2 millennia later, Galileo completely flipped Aristotle's idea on its head. Galileo looked at that exact same box being pushed across the floor, but he ran a thought experiment. He imagined making the floor perfectly smooth and polished. Then he imagined adding grease to it. He realized that as you reduce the resistance between the box and the floor, you need less and less force to keep it moving. Galileo basically introduced a hidden opposing force that Aristotle completely missed: friction. He realized that if you could somehow reduce friction to absolute zero, a moving object would just keep moving. It would travel at a constant speed forever because there'd be literally no force slowing it down. So constant speed, he argued, was just as natural a state as being at rest, a total game changer. And that brilliant realization brings us to section 2, Newton's 3 laws. Enter Isaac Newton. This guy took Galileo's profound insights about friction and natural states, and he formalized them into a comprehensive, cohesive theory of motion. We're talking about his 3 universal laws, published in his famous Principia. These laws quite literally laid the absolute groundwork for classical mechanics. They are the underlying rules that dictate how everything in our physical universe interacts. Let's break these laws down step by step, shall we? Step 1 is the first law, which you've probably heard called the law of inertia. This one directly echoes Galileo. Basically, every object continues in a state of rest, or uniform velocity, unless it's acted on by a resultant force. Inertia is essentially just an object's stubbornness, It's that built-in property to resist any change in its motion. Then we have step 2, the second law, which explains exactly what happens when a force is applied. It causes acceleration, or a change in velocity. And finally, step 3 is the third law, which governs the actual interactions between different objects. So, the real crucial point of the second law is this incredibly elegant, super famous relationship, F equals ma. Force equals mass times acceleration. This simply tells us that the acceleration of an object is directly proportional to the resultant force applied to it. But it also introduces mass mathematically. Mass is the measure of that inertia we were just talking about. So the bigger the mass, the more difficult it is to change its velocity. Think about it. If you want to accelerate a heavier object at the exact same rate as a lighter one, this equation proves you're going to need a much, much larger force. And our rocket here brilliantly illustrates the third law. Remember, whenever one object exerts a force on another, that second object exerts an equal and opposite force right back on the first one. The truly crucial detail to remember here is that these 2 forces are acting on entirely different objects. Let's look at this space rocket launching. To actually propel itself upwards, the rocket exerts a massive, massive downward force on its exhaust gases. In response to that, those exhaust gases exert an equal and opposite upward force on the rocket. It is not pushing against the ground, and it's not pushing against the air. The interaction between the rocket and the expelled gas itself is what accelerates it all the way into orbit. How cool is that? Moving right along, let's dive into section 3, the momentum concept. You can really just think of linear momentum, which is P equals mv, as the sheer quantity of motion that an object possesses. Because it multiplies mass and velocity together, a slow-moving, super heavy truck and a fast-moving, incredibly light bullet can actually both have immense momentum. It's also a vector quantity, meaning the direction it's going absolutely matters. And, connecting this all the way back to Newton's first law, if an object maintains a uniform velocity and its mass doesn't change, well, its momentum remains perfectly constant. And that right there is the fundamental foundation of the principle of conservation of momentum.
Now, it turns out that resultant force is actually equal to the rate of change of momentum. Believe it or not, this is how Newton originally thought about his second law, and it's exactly how it's used in complex problem solving today. Sure, F equals ma is super useful, but acceleration is really just the rate of change of velocity. So if you multiply that by mass, force literally becomes the rate of change of momentum. What this means, in plain English, is that the magnitude of a force applied to an object is directly proportional to how fast you are changing that object's momentum.
Okay, let's clear up a huge common misconception in Section 4, mass versus weight. We really need to look at this clear distinction because people mix this up all the time. In physics, mass is an intrinsic property of an object. It's the absolute measure of an object's inertia, again, how much it resists a change in motion, and it is strictly measured in kilograms. Listen to this. Your mass is the exact same whether you are sitting here on Earth, bouncing around on the moon, or just floating out in deep space. Weight, however, is a completely different story. Weight is specifically the effect of a gravitational field acting on a mass. Because weight is an actual force pulling down on an object, it's measured in newtons, not kilograms. Because weight is a force, we can just apply Newton's second law to calculate it. W equals mg. Weight equals mass multiplied by the acceleration of freefall. If we completely ignore air resistance for a second, all objects released near the Earth's surface fall with a constant acceleration. We denote this as g, and it measures 9.81 meters per second squared. So if you want to find the true weight of a 1 kilogram mass here on Earth, you just multiply 1 by 9.81. That gives you a weight of 9.81 newtons directed straight towards the center of the Earth. And finally, that brings us to Section 5, measuring our world. To actually measure these properties in real life, we use two entirely different types of devices. A laboratory beam balance physically directly compares two masses. It relies on the equilibrium of the beam, so when it's perfectly horizontal, the moment of the weight on one side exactly equals the moment on the other. And because gravity affects both sides equally, the masses themselves must be equal. However, a top pan balance, which is very similar to a commercial spring balance, uses an internal spring mechanism to measure the downward force acting on the pan, which means it's measuring weight. And that leads us to our final mind-bending twist of the day. You know that spring scale at the supermarket fruit counter? The one you use for produce? Yeah, it's actually measuring weight. It is measuring the gravitational pull on your groceries. But because everyday shoppers don't walk around speaking in newtons, the scale manufacturers basically do the math for us behind the scenes. The scale is cleverly calibrated to just display the reading in kilograms. So when you bag up what the scale says is 5 kilograms of mangoes, the machine is actually sensing 49 newtons of downward gravitational force, and it's just simply translating that back into mass units for your convenience. Pretty sneaky, right? So, I'm going to leave you with this final thought. Next time you step on a bathroom scale, are you actually measuring your body's inertia? Or just the Earth's gravitational pull? Really think about it. Keep that absolutely crucial distinction between mass and weight in mind as you navigate the physical world. And as you go about your day to day, consider how many other simple, everyday facts of life are just profound physics concepts waiting to be properly explained.